Section 6 is about volume and moles, looking at Avogadro's law. We'll use Avogadro's law to determine the amount or the volume of a gas when the pressure and temperature do not change. Avogadro's law was formulated by Amedeo Avogadro in 1811, and it states that the volume of a gas is directly related to the number of moles of gas when the temperature and pressure are held constant. Here's another equation. Again, there's no change in pressure or temperature, so we can say V1 over N1 equals V2 over N2, and N is the number of moles of a gas. The volume of a gas is directly related to the number of moles of a gas. If the number of moles is doubled, then the volume must be doubled. Notice here, I have 1 mole of gas, and it is taking up 1 liter of space. Notice that my volume doubled when my moles doubled. Let's look at a sample problem. A weather balloon with a volume of 44 liters, so that's our volume 1, it's filled with 2 moles of helium. That's our N1. What is the final volume in liters? So it's asking for V2. If 3 moles of helium are added to give a total of 5 moles of helium, that would be our N2. We want our total if the pressure and temperature do not change. So let's set this up. V1 over N1 equals V2 over N2. And my V1 is 44 liters, and that's with 2 moles. So let's figure out what V2 would be when we have 5 moles. All right, let's cross multiply just like we did with the other gas laws. I'm going to do 44 times 5, which is 220, and that's equal to 2 times V2. Now let's get V2 by itself and divide both sides by 2. V2 is equal to 110, and our volume should be in liters, 110 liters. We should have, let's see, that's 2 sig figs, 2 sig figs, 2 sig figs, and that's 2 sig figs. Now at standard temperature and pressure, which we would abbreviate STP, standard temperature and pressure, 1 mole of any gas occupies a volume of 22.4 liters, which is approximately equal to the volume of 3 basketballs. The volumes of gases can be compared at standard temperature and pressure when they have the same number of moles of gas. Standard temperature is exactly 0 degrees Celsius or 273 Kelvin. Standard pressure is exactly 1 atmosphere or 760 millimeters of mercury. So we could say that at standard temperature and pressure, so at 0 degrees Celsius and at a pressure of 1 atmosphere, that 1 mole of helium, 1 mole of oxygen, 1 mole of nitrogen, all at that same temperature and the same pressure. Now there's different grams of each of these. Remember, 1 mole of helium has a mass of 4.003 grams. We'd look at the periodic table. 1 mole of oxygen gas, so 2 oxygens would have a mass of 32. 1 mole of N2, which is 2 nitrogens added together. The masses are different, but it's 1 mole of each of those substances have a volume of 22.4 liters. We can then use that molar volume at STP as a conversion factor, and it can be used to convert between moles of gas and volume in liters. So 1 mole of gas is equal to 22.4 liters, and we can write it like this with liters on top and moles on the bottom, or we can flip-flop it around. We can say 1 mole of gas takes up 22.4 liters. Let's look at a sample problem. We are given that we have 64 grams of oxygen gas at STP. We want to find out how many liters of oxygen gas that is. If we're given grams, we need to go to moles. So the very first step, we're going to take 64.0 grams of O2. Anytime we start with grams, we got to get to moles. And we look at the molar mass. So for 1 mole of O2, 16 plus 16 would be 32 grams of O2. So that gets rid of my grams of oxygen. Now I'm at moles. And we can go from moles to liters because we remember that 1 mole of gas is equal to 22.4 liters, or we can have the liters on top and moles on the bottom. So what do we need here? Well, because we're rid of our grams, I now need to get rid of moles of O2. So I need to have 1 mole of O2 on the bottom and 22.4 liters of O2 on top. So now we just need to do 64 times 1 times 22.4, all divided by 32. And notice that moles of O2 cancel, and that will leave us with liters of O2. And my calculator gave me 44.8 liters of oxygen. Make sure that you set it up right and that we had grams and grams to cancel out, moles of oxygen to cancel out, and that we ended with 3 significant figures. And this is, of course, at standard temperature and pressure. Take a minute to look over the learning goal, and then we're moving on to section 7. This section is about the ideal gas law. We will use the ideal gas law equation to calculate an unknown pressure, volume, temperature, or number of moles of a gas when given 3 of the 4 values in the ideal gas law equation. Calculate the molar mass of a gas. The ideal gas law is a combination of the 4 properties: pressure, volume, moles, and temperature, written as a single expression. You need to know this. PV equals nRT. Rearranging the ideal gas law equation shows that the 4 properties are equal to the gas law constant, R. R is 0.0821 liters atmospheres per moles Kelvin. So this is something that you're going to want to know. This R is a constant. Notice that this is for when we have liters, atmospheres, moles, and Kelvin for our volume, our pressure, our moles, and our temperature. Now, we have done problems where we used millimeters of mercury instead of atmospheres. So if that's the case, if our pressure is in a different unit, we would need to use a different R. If we're using millimeters of mercury, we would use this R constant. So it is important to make sure that you are aware of what units are being used, because we would need to use the correct R constant that goes with that unit. And the only difference between these two, notice that our volumes are both in liters, our amount is in moles, our temperature is in Kelvin. But if our pressure is in atmospheres, this is the R that we would use. If our pressure is in millimeters of mercury, then this is the R that we would use. Let's do a sample problem. Dinitrogen oxide, N2O, also called laughing gas, is an anesthetic used in dentistry. What is the pressure in atmospheres? So we need to find P in ATMs of 0.350 moles, so that's our N, of N2O, at 22 degrees Celsius, so that's our temperature, but we need to add 273, so that would be 295 Kelvin, in a 5-liter container. That's our volume. We can use our PV equals nRT, ideal gas law equation. We're going to find P. We want P in ATMs. We know our volume, we know N, we know temperature, and we're going to use the R that has atmospheres in it. All right, I set it up here. PV equals nRT. We don't know P. We know our volume is 5 liters, equals, this is our N, this is our R. I used the R that had ATMs in it, and that's our temperature, 295 Kelvin. Now notice how our liters and liters will cancel from that R. The moles and the moles will cancel, and the Kelvin and the Kelvin will cancel. So the only unit left will be ATMs, which is what we're looking for as our pressure. So to get pressure by itself, we just need to get rid of this 5 liters. So let's divide this side by 5 liters. That'll cancel out. And then we'll divide this whole thing by 5 liters. So 0.350 times 0.0821 times 295, and then divide it by 5. And my calculator spit out 1.695365. All of my beginning numbers all had 3 significant figures, so let's end with 3. I'll go 1, 2, 3. That 5 will round that up, so I'm going to end up with 1.70 ATMs. We could have also rearranged our equation to solve for pressure. If you would have rather said, you know what, I just want to get P by itself, so I'm going to divide both sides by V. And so you can plug it right into P is equal to nRT divided by V. If you would rather do it that way, you'll get the same answer. The ideal gas law is also used to determine the molar mass of a gas. Dividing the mass of a gas by the number of moles of the gas gives us the molar mass, right? Molar mass is grams per mole. So if I know the mass of the gas and I divide it by moles of the gas, that would give me the molar mass. Let's try an example problem. What is the molar mass in grams per mole of a gas if a 3.16 gram sample, so this is my mass, at 0.750 atm, that's a pressure, 45 degrees Celsius, that's a temperature, so let's add 273 to get to Kelvin. That would be 318 Kelvin. And it occupies a volume of 2.05 liters. That is our volume. Let's look at what we know. I know pressure, I know volume, I know temperature, and I know R. It's the constant, and I'm going to use the constant that has ATMs. So the only thing that I don't know that I can find is my number of moles. And once I find my moles, I can then take my mass and divide it by my moles to find the molar mass. So let's do that. Here we took PV equals nRT and we wanted to solve for N. So we wanted to get rid of what was attached to N. So we divided both sides by RT. So PV divided by RT would equal N. Then they plugged in the pressure, which is 0.75, the volume, 2.05, and then divided by the R value that had ATMs, which is 0.0821, and the temperature, 318 Kelvin. And we should get, with three significant figures, 0.0589 moles. This is our N. We could have also solved it by just plugging in everything and solving for N. If we set it up like this, we've got PV equals N, and this is R, and that's T. To get N by itself, we're going to divide by 0.0821 times 318. If I multiply those two together, my calculator tells me that I got 26.1078. That'll get rid of these, leaving me with just N. So I'm going to divide by 26.1078, and that would leave me with N is equal to, we should get the same answer. And the last step to find molar mass, we need to take the mass in grams and divide it by moles. And we were told that our mass was 3.16 grams and our moles 0.0589 moles, and I got 53.7 grams per mole. That's its molar mass. Take a minute to make sure that you feel comfortable with this learning goal using the ideal gas law equation.